The terrifying truth about how cold space really is will fundamentally change the way you see your own existence. Because matter shouldn't exist like this. And by the end of this, you'll understand exactly why scientists lose sleep over that fact. Right now, as you listen to these words, every atom in your body is vibrating. Every molecule in the air around you is shaking. The coffee in your mug, the glass of your screen, the blood pulsing through your veins, the calcium in your bones, all of it trembling with invisible energy. We call that energy heat. It is the kinetic motion of particles, the ceaseless jittering of atoms, the vibration that separates the living from the lifeless and the warm from the void. And without it, you would not just die. You would stop being a thing at all. We rarely think about heat this way. We think of it as comfort, as warmth on a cold day, as the glow of a fireplace or the steam rising from a bowl of soup. But heat is not comfort. Heat is motion. It is the frantic, ceaseless jittering of atoms, the invisible dance of particles that make solid things feel solid, that makes liquids flow, that makes gases expand and fill a room. Every sensation you have ever felt, the warmth of another person's hand, the sting of a sunburn, the chill of an ice cube against your lip, all of it is information about how fast particles are moving. Your nerves are speedometers for atoms. Your entire sensory experience of temperature is, at its foundation, a report on the kinetic energy of the matter touching your skin. That is the terrifying truth about how cold space really is. Not that it will freeze you. Not that it will chill you to the bone, but that the cold of the universe is so absolute, so fundamental, that at its deepest extreme, matter itself forgets what it is. Atoms lose their identity. Particles overlap and merge into a single ghostly blur. The laws of physics as we know them begin to dissolve. And the question that should keep you awake at night is this: what happens to the fabric of reality when heat, the very heartbeat of existence, fades away entirely? We are going to answer that question. And to do it properly, we are going to travel from the warmth of your living room to the coldest places that have ever existed, both in nature and in the laboratory. We are going to watch what happens to the human body when it is stripped of every protection and exposed to the true vacuum. We are going to descend the temperature scale, degree by degree, past the point where water freezes, past the point where nitrogen becomes a liquid, past the point where helium surrenders its freedom, into a realm where the very concept of separate objects begins to break down. We are going to visit a dying star that has somehow become colder than the afterglow of the Big Bang. We are going to watch atoms lose their individuality and merge into a single quantum ghost. And then, at the very end, we are going to look forward, far forward, past the death of the last star, past the evaporation of the last black hole, into the final eternal winter that awaits the cosmos. To begin to answer that question, we need to do something uncomfortable. We need to strip away every layer of protection that stands between your warm, living body and the true nature of the void. Because space is not just empty. It is a kind of emptiness that actively pulls the warmth out of you. Not fast, not violently, but with a patience that stretches across eternity. The void does not attack. It does not grab. It simply offers an infinite reservoir of cold, and the laws of physics do the rest. We are so accustomed to being surrounded by matter, by air and water and solid ground, that we forget what a privilege that is. On Earth, you are never more than a few molecules away from something. Even on the highest mountain, in the thinnest air, there are still trillions of molecules in every breath you take. But in the space between stars, there may be only a few atoms per cubic centimeter, In the space between galaxies, even fewer. The void is not just empty. It is emptier than anything you can create in a laboratory on Earth. The best vacuum chambers built by human engineers still contain roughly 1 million molecules per cubic centimeter. Interstellar space does better than that by a factor of 1,000. And intergalactic space is emptier still, approaching a genuine nothingness that makes our best laboratory vacuums look crowded. So let us start there. Let us start with you, floating, alone, without a suit, without a ship, without anything between your skin and the coldest environment that exists. The first thing that would happen is not what most people expect. You would not freeze. That is the myth that Hollywood loves. The image of an astronaut turning to ice the instant a helmet cracks open. But reality is stranger than that, and in some ways far more unsettling. The moment your body is exposed to the vacuum of space, the first crisis is not temperature, it is pressure, or rather, the complete absence of it. On Earth, the atmosphere pushes down on every square inch of your skin with about 14 pounds of force. You do not feel it because your body has spent its entire existence pushing back. But remove that pressure in an instant, and the balance breaks. The gases dissolved in your blood would begin to form tiny bubbles. Not boiling, not the way water boils on a stove, but something called ebullition. The reduced pressure allows dissolved gases to come out of solution, the same way carbon dioxide fizzes out of a soda when you crack the seal. Nitrogen, which makes up a significant portion of the gas dissolved in your blood at normal atmospheric pressure, would bubble out into your tissues and bloodstream. Your tissues would swell. Your body would puff up, expanding to roughly twice its normal volume. Not to the point of exploding, because human skin is remarkably tough, but enough to stretch and distort in ways that would feel deeply wrong if you were still conscious enough to register the sensation. The swelling would be most dramatic in the areas of your body with the loosest skin. Your hands, your feet, your abdomen. The gas bubbles forming in your tissues would not be like the bubbles in a glass of champagne, harmlessly rising and popping. They would be interstitial, forming in the spaces between cells, in the fluid, surrounding your organs, in the fine capillaries of your circulatory system. If you have ever heard of decompression sickness, the bends, the condition that afflicts scuba divers who surface too quickly, this is the same phenomenon, but taken to its absolute extreme. A diver with the bends has nitrogen bubbles forming in their joints and bloodstream because they ascended faster than their body could gradually release the dissolved gas. In a full vacuum, every dissolved gas in your body would come out of solution simultaneously. The pain would be extraordinary, but it would not last long. The moisture on your tongue, in your eyes, on the surface of your lungs, that would begin to evaporate almost immediately, not because it is hot, but because in a vacuum, water transitions from liquid to vapor at incredibly low pressures. You would feel the saliva on your tongue start to bubble. The last astronaut who experienced anything close to this was a test subject at NASA in 1965, when his pressure suit sprang a leak inside a vacuum chamber. He remained conscious for about 14 seconds. The last thing he remembered before blacking out was the sensation of the water on his tongue beginning to boil. 14 seconds. That is how long you would have to understand what was happening to you. After that, the oxygen remaining in your bloodstream would be consumed. Your brain would go dark. Unconsciousness would arrive like a curtain falling. And from that point forward, everything that happened to your body would happen without you knowing. It is worth pausing on that 1965 incident, because it is one of the only data points we have about what actually happens to a conscious human being in a vacuum. The test was being conducted at the Manned Spacecraft Center in Houston, and the subject was an experienced technician whose name has never been publicly disclosed. He was wearing a full pressure suit inside a vacuum chamber when the suit suffered a catastrophic leak. The chamber was pumped down to near vacuum conditions. He felt the air rushing out of his suit. He felt the pressure dropping. And then he felt something that no other living person had ever felt, or at least lived to describe. The saliva on his tongue began to bubble as the water transitioned to vapor in the near-zero pressure. He was aware of this sensation for a few seconds before losing consciousness. The chamber was repressurized within about 30 seconds, and he recovered fully. But his account of those last conscious moments remains one of the most vivid first-hand descriptions of what it feels like to be at the boundary between the pressurized world of the living and the depressurized world of the void. The incident also confirmed something that scientists had suspected, but never proven directly. The human body does not explode in a vacuum. The skin, the largest organ, is strong enough to contain the internal pressure of the body, even when external pressure drops to zero. You would swell, yes. Your tissues would puff with gas. But the structural integrity of your body would hold. You would not burst like a balloon. You would simply bloat, gasp, and fade. Here is where the cold finally enters the story, but not in the way you might imagine. In your everyday life, when you step outside on a winter morning, the cold air around you pulls heat from your skin through two main processes. The first is conduction. The air molecules touching your skin vibrate against your skin molecules and steal some of their energy. The second is convection. The warmed air near your body rises and is replaced by fresh cold air, creating a constant cycle of heat removal. In space, neither of these processes exists. There is no air to conduct heat away from your body. There is no fluid to carry warmth upward and pull cold downward. The vacuum is, in a very real sense, the best insulator in the universe. If you sealed a thermos with a perfect vacuum inside, it would keep your coffee hot for an extraordinarily long time. And that same principle applies to your body floating in the void. The vacuum itself cannot steal your heat through contact because there is nothing to make contact with. But you would still lose heat, slowly, quietly, through the only mechanism that works in the emptiness between stars: radiation. Every object in the universe that has a temperature above absolute zero emits electromagnetic radiation. It is not optional. It is not a choice the object makes. It is a fundamental consequence of having atoms that move. The faster those atoms vibrate, the more radiation they emit. Your body, at roughly 37 degrees Celsius, or 310 Kelvin on the absolute temperature scale, radiates energy primarily in the infrared spectrum. You are, in a very real sense, glowing right now. You are a lantern of invisible light, broadcasting your warmth into the room around you. On Earth, that does not matter much, because the walls and air and furniture around you are radiating energy back at you in roughly equal measure. The exchange is balanced. You stay warm. In deep space, the equation changes. The background temperature of the universe is approximately 2.7 Kelvin. That is 2.7 degrees above absolute zero, negative 270 degrees Celsius, and your body at 310 Kelvin would be radiating its heat into that 2.7 degree void. The difference is enormous. The rate of radiative heat loss depends on the fourth power of the temperature difference, which means the gap between your body temperature and the background temperature of space drives a significant outward flow of energy. But even so, radiation is a slow process compared to what we are used to on Earth. Without conduction or convection to help, your body would cool gradually. Not in seconds, not in minutes. Over hours, your temperature would drift downward, degree by degree, as your infrared glow carried your life energy out into the dark. This fourth power relationship is described by something called the Stefan-Boltzmann law, and it is one of the most important equations in all of thermal physics. It tells us that the total energy radiated by an object every second is proportional to the fourth power of its absolute temperature. Double the temperature of an object, and it radiates 16 times as much energy. Triple the temperature, and it radiates 81 times as much. This is why the sun, at roughly 5,800 Kelvin, pours out such extraordinary quantities of energy. And it is why your body, at a comparatively modest 310 Kelvin, radiates energy at a much gentler rate. The Stefan-Boltzmann law also explains something that might seem paradoxical at first. If you were floating in space in the shade, away from any star, you would cool slowly through radiation. But if you were floating in direct sunlight, without a spacesuit, you would have an entirely different problem. The sun delivers about 1,400 watts of energy per square meter at Earth's distance. Without an atmosphere to filter the ultraviolet and infrared, that energy would slam into your exposed skin at full intensity. The side of your body facing the sun would heat rapidly, potentially suffering severe burns within seconds. Meanwhile, the side facing away from the sun would be radiating into the void and cooling. You would simultaneously be too hot on one side and too cold on the other. This is exactly what happens to the moon, where the surface facing the sun bakes at over 120 degrees Celsius, while the shadowed surface, mere meters away, plunges below -170. This temperature split is one of the defining challenges of spacecraft engineering. Every satellite, every space station, every probe sent beyond Earth's atmosphere must contend with this brutal thermal asymmetry. The side facing the sun absorbs enormous energy. The side facing deep space loses energy to the void. Without active thermal management systems, heat pipes, radiators, insulation, and reflective coatings, a spacecraft would quickly overheat on one side and freeze on the other. The International Space Station, for example, uses ammonia-filled heat pipes to transfer excess heat from its sun-facing panels to large radiators that dump that energy into space as infrared radiation. It is, in essence, a machine for managing the thermal violence of the vacuum. You would be long dead from suffocation before you even began to feel cold. Your blood would still be liquid inside your veins, because the pressure of your circulatory system is enough to keep it from boiling. Your skin might develop a thin layer of frost from the rapid evaporation of surface moisture, but your core would remain warm for a surprisingly long time. You would drift, a slowly cooling object, radiating your last warmth into a universe that does not care. This is what makes space so profoundly different from any cold environment on Earth. A winter in Antarctica can kill you in minutes because the air is a ruthlessly efficient thief of heat. The wind alone can strip warmth from exposed skin faster than your body can produce it. But the vacuum of space is not a thief. It is a void. It does not reach in and grab your heat. It simply waits, endlessly patient, for your warmth to radiate away on its own. And it will. Given enough time, it always will. There is a common misconception that space has a single temperature, that the void is uniformly cold everywhere. This is not true. The temperature you experience in space depends entirely on where you are and what is near you. In low Earth orbit, astronauts on the International Space Station cycle between sunlight and shadow every 90 minutes. When the station faces the sun, its hull absorbs solar radiation, and the exterior temperature rises to roughly 121 degrees Celsius. When it passes into the shadow of the Earth, that temperature plunges to negative 157 degrees Celsius. The swing of nearly 280 degrees happens in about 45 minutes. This is why thermal management is such a critical discipline in spacecraft design. The vacuum does not have a temperature of its own. It is a transparent medium through which radiation passes. The temperature of any object in space is determined by the balance between the radiation it absorbs and the radiation it emits. Deep in interstellar space, far from any star, the situation is different. There, the only significant source of radiation is the cosmic microwave background, and an object left to its own devices will eventually cool to the background temperature of 2.7 Kelvin. This is why astronomers sometimes describe deep space as being approximately 2.7 degrees above absolute zero. It is not that the vacuum has that temperature. It is that any object placed in the vacuum, far from any star, will equilibrate to that temperature over time. The Moon offers a perfect demonstration of this principle. When the lunar surface faces the Sun, temperatures climb to roughly 120 degrees Celsius, hot enough to boil water. But when that same surface rotates into shadow, the temperature plunges to negative 130 degrees Celsius or lower. The swing is extreme, roughly 250 degrees in either direction, because there is no atmosphere to moderate the transition, no air to trap heat during the night, no blanket of gas to soften the blow, just radiation in and radiation out. The surface heats when photons arrive from the Sun, and it cools when those photons stop coming, and the surface radiates its stored energy into the blackness. Now here is the part that should change how you think about all of this. That 2.7 Kelvin background temperature of the universe is not just a number. It is a relic, a fossil frozen in light from the earliest moments of existence. It is called the cosmic microwave background, and it is the afterglow of the Big Bang itself. Roughly 380,000 years after the universe was born, the cosmos cooled enough for the first atoms to form. Before that moment, the universe was a blinding fog of charged particles and photons, so dense that light could not travel more than a short distance before slamming into something. But when neutral atoms formed, the fog lifted. Light was free to travel. And the photons released at that moment have been traveling ever since for nearly 14 billion years, stretching and cooling as the universe expands around them. When those photons were first released, their temperature was roughly 3,000 Kelvin. The universe was glowing like the surface of a red star. But as space itself expanded, the wavelengths of those photons stretched along with it. They shifted from visible light to infrared, from infrared to microwave. And today, that ancient light fills every cubic centimeter of space with roughly 400 photons, all vibrating at a frequency that corresponds to a temperature of 2.700 Kelvin. You are bathed in it right now. It passes through the walls of your home, through your body, through the earth itself. It is everywhere, and it is always there. The faintest whisper of the universe's first scream. The discovery of this radiation is one of the great accidental triumphs in the history of science. In 1964, two radio astronomers named Arno Penzias and Robert Wilson were working at Bell Laboratories in New Jersey. They were using a large horn-shaped antenna, originally built for satellite communications, to map radio signals from the Milky Way. But no matter where they pointed the antenna, no matter what time of day or night, no matter what season, they detected a persistent, uniform background of microwave noise. It came from every direction equally, It was not associated with any known star, galaxy, or radio source. They cleaned the antenna. They checked the electronics. They even removed a pair of pigeons that had nested inside the horn and scrubbed away the droppings, thinking that the bird waste might be causing interference. Nothing worked. The noise persisted. At the same time, a group of physicists at Princeton University, led by Robert Dicke, was building a detector specifically to search for the predicted afterglow of the Big Bang. When Penzias and Wilson learned of the Princeton group's work, the connection became clear. The mysterious background noise was not a malfunction. It was the cosmic microwave background radiation, the leftover light from the birth of the universe, the oldest signal in all of existence, arriving from every direction because it was emitted everywhere, simultaneously, 13.8 billion years ago. Penzias and Wilson received the Nobel Prize in Physics in 1978 for their discovery. Subsequent missions, including NASA's COBE satellite in 1989 and the European Space Agency's Planck satellite in 2009, measured the CMB with extraordinary precision. The spectrum is a nearly perfect blackbody curve at a temperature of 2.725 Kelvin, with fluctuations of only a few parts per 100,000. These tiny variations, mapped across the entire sky, reveal the density fluctuations in the early universe that would eventually grow, through gravitational attraction over billions of years, into the galaxies, galaxy clusters, and cosmic web of structure that we observe today. Every galaxy you have ever seen in a photograph grew from a seed planted in the microwave background. That 2.7 degrees is, in a sense, the temperature floor of the cosmos. It is the minimum temperature that any object in the natural universe can reach simply by sitting in the void and radiating its heat away. Because no matter how long you wait, no matter how much warmth you lose, you will always be absorbing those ancient photons. They pour in from every direction, a gentle bath of energy left over from creation. And as long as they exist, no natural object can cool below their temperature. But here is the puzzle that drives this entire story forward. There is a place in the universe, a real, observable, confirmed place, that is colder than that background glow, colder than the afterglow of the Big Bang, colder than the universe was ever supposed to be in nature. And the way it got there challenges our understanding of what cold really means. Before we go to that place, though, we need to understand the scale of what we are talking about. We need to understand what temperature actually is, at its most fundamental level. Because temperature is not what most people think it is. It is not a substance. It is not a thing that flows into or out of objects. It is a measurement of motion. Specifically, it is a measurement of how fast the particles inside a substance are vibrating, rotating, and bouncing around. This is a surprisingly recent understanding. For most of human history, people thought of heat as a fluid, a weightless, invisible substance called caloric that flowed from hot objects to cold ones like water flowing downhill. The caloric theory was elegant and intuitive. A hot iron bar contained a lot of caloric. A cold glass of water contained little. When you placed the iron in the water, caloric flowed from the bar to the water until both reached the same temperature. It explained a great deal of everyday experience, and it was completely wrong. The true nature of heat was established in the 1840s and 1850s by James Joule, Rudolf Clausius, and others who showed that heat is a form of energy, specifically the kinetic energy of molecular motion. When you heat a gas, you are making its molecules move faster. When you cool it, you are slowing them down. Temperature is simply a measure of the average kinetic energy of the particles in a substance. Nothing more, nothing less. When you touch a hot stove, you are not touching heat. You are touching a surface whose atoms are vibrating so violently that they transfer their kinetic energy into the molecules of your skin, causing damage. When you hold an ice cube, you are not holding cold. You are holding a substance whose molecules are barely moving at all, and the energy is flowing from your warm hand into the sluggish ice, causing it to melt. Temperature is motion. Heat is the transfer of that motion from one place to another. Cold is not a thing. Cold is the absence of a thing. Cold is what remains when motion slows. This idea was formalized in the 1800s by a scientist named William Thomson, better known as Lord Kelvin. He proposed a temperature scale that starts at the very bottom, at the point where all thermal motion ceases entirely. He called it absolute zero, 0 Kelvin, negative 273.15 degrees Celsius, negative 459.67 degrees Fahrenheit. And it is not just a number on a scale. It is a wall, a hard, fundamental boundary in physics that nature refuses to let us cross. The story of how we discovered this boundary is itself a story of cold. In the late 1800s and early 1900s, scientists were engaged in a fierce race to reach lower and lower temperatures. The tools were rudimentary by modern standards, relying on cascading stages of gas compression and expansion to wring heat out of substances 1 degree at a time. In 1898, the Scottish chemist James Dewar became the first person to liquefy hydrogen, reaching a temperature of 21 Kelvin, negative 252 degrees Celsius. It was a triumph of engineering, but it was not cold enough. The real prize went to the Dutch physicist Heike Kamerlingh-Onnes. In 1908, after years of painstaking work, he became the first to liquefy helium, using a series of pre-cooling stages to push below the boiling point of hydrogen and into uncharted thermal territory. He reached 4.2 Kelvin. By further reducing the pressure of the liquid helium, he pushed even lower, touching 1.5 Kelvin. These were the coldest temperatures ever achieved on Earth, and they earned him the Nobel Prize in 1913. More importantly, they opened the door to a new realm of physics. At these temperatures, Kamerlingh-Onnes discovered superconductivity, the ability of certain materials to conduct electricity with absolutely zero resistance. It was the first hint that the near-zero world was home to phenomena that had no equivalent at ordinary temperatures. Since then, the race to cold has continued with ever more sophisticated tools. Laser cooling, magnetic trapping, evaporative cooling, and nuclear demagnetization have pushed the boundaries further and further. Each new low-temperature record has revealed new physics. Superfluidity was discovered at 2.17 Kelvin. Bose Einstein condensation was achieved at billionths of a Kelvin, and the current world record, set in 2021 at the University of Bremen, stands at 38 picokelvin, roughly 38 trillionths of a degree above absolute zero. At that temperature, atoms are moving so slowly that their de Broglie wavelengths extend to macroscopic scales. The quantum nature of matter, usually hidden at the subatomic level, becomes visible to the naked eye. At absolute zero, in theory, every atom in a substance would be in its lowest possible energy state. The vibrations would stop, the rotations would cease. The bouncing and jostling of particles would fall silent. It would be a kind of perfect stillness, a silence so complete that the very concept of motion would lose its meaning. But here is the strange thing. You cannot get there. Not just in practice, not just because our refrigerators are not powerful enough. You cannot get there in principle. The third law of thermodynamics, first proposed by Walter Nernst in 1912, states that it is impossible for any process to bring a system to absolute zero in a finite number of steps. Every time you remove some heat from an object, you get a little closer, but the closer you get, the harder it becomes to remove the next bit of heat. The effort required increases without limit. It is like trying to reach the end of a road that stretches farther away. With every step you take, you can get extraordinarily close. Scientists have cooled matter to within billionths of a degree of absolute zero. But the last infinitesimal fraction, the final breath of motion, cannot be taken away. Absolute zero is a limit, not a destination. It is the horizon of cold. Imagine trying to empty a swimming pool with a bucket. The first few buckets are easy. You scoop out the water and the level drops noticeably. But as the pool gets shallower, each bucket removes a smaller fraction of what remains. And then imagine that the pool has no bottom, that as you scoop, new water seeps in from below, slower and slower, but never stopping entirely. You can get the pool nearly empty. You can reduce the water to a thin film, then to droplets, then to individual molecules clinging to the surface. But you can never get every last molecule. There is always one more. This is the nature of the approach to absolute zero. Each step removes less heat than the one before. Each step requires more energy, more ingenuity, more sophisticated equipment. And the finish line recedes forever. In 2017, over 100 years after Nernst first proposed his law, physicists Louis Massanes and Jonathan Oppenheim at University College London published a mathematical proof confirming what Nernst had suspected. Using techniques from quantum information theory, they showed that reaching absolute zero would require both an infinite number of steps and an infinite reservoir of energy. In other words, it would take a universe with unlimited resources and unlimited time. And even then, quantum mechanics has something to say about it. The Heisenberg uncertainty principle, one of the foundational rules of quantum physics, tells us that you cannot simultaneously know both the exact position and the exact momentum of a particle. The more precisely you pin down where a particle is, the less you can know about how fast it is moving, and vice versa. This means that even at absolute zero, particles cannot be perfectly still. There will always be a residual jitter, a tiny irreducible vibration called zero-point energy. The atoms may slow to an almost imperceptible crawl, but they will never stop moving entirely. Even in the quietest, coldest state imaginable, the universe insists on a whisper of motion. Zero-point energy is not a small or negligible effect. It is the reason that helium remains a liquid all the way down to absolute zero at normal pressures. Every other element in the periodic table freezes solid at low enough temperatures, its atoms locking into a rigid crystal lattice as thermal motion ceases. But helium's atoms are so light, and its zero-point energy is so large relative to the weakness of its interatomic forces, that the residual quantum jitter is enough to prevent the atoms from settling into a fixed structure. Liquid helium, at temperatures near absolute zero, is a direct visible consequence of the uncertainty principle. It is a substance that refuses to freeze because the laws of quantum mechanics forbid its atoms from sitting still. This is one of the most profound realizations in modern physics. Stillness does not exist, not truly. Not at the deepest level of reality. There is always movement. There is always a tremor. The universe is fundamentally restless, and no amount of cooling can change that. The vacuum of space is not empty. It seethes with quantum fluctuations, virtual particles popping into and out of existence, fields oscillating at their zero-point values. Even in the void between galaxies, in the darkest, coldest, most desolate reaches of the cosmos, there is activity at the quantum level. The universe has a floor, and that floor is not still, it hums. So when we talk about the cold of space, we are talking about a spectrum of motion. At the warm end, atoms dance furiously, colliding and rebounding with tremendous energy. At the cold end, they barely move at all, drifting in slow, ghostly orbits. And at the very limit, at the theoretical floor of temperature, they are reduced to the quietest state that physics allows, vibrating with just enough energy to satisfy the uncertainty principle. Now let us talk about the Kelvin scale in a way that makes the numbers feel real. Room temperature, the comfortable warmth of your living space, is about 293 Kelvin. The freezing point of water is 273 Kelvin. The coldest temperature ever recorded on the surface of the Earth was in Antarctica in 2010, roughly 184 Kelvin, or negative 89 degrees Celsius. That temperature was measured by satellite over the East Antarctic Plateau, a vast, high-altitude ice sheet so remote and inhospitable that no human being has ever stood at the exact spot where the record was set. At that temperature, a glass of boiling water thrown into the air would freeze before it hit the ground. Steel becomes brittle. Rubber shatters like glass. The moisture in a single breath would crystallize into a cloud of ice particles before it traveled a foot from your lips. Liquid nitrogen, the stuff used to flash freeze biological samples and create clouds of theatrical fog, boils at 77 Kelvin. At that temperature, ordinary air would condense into a liquid. Oxygen would pool on the floor like water. The familiar gases that fill our lungs and sustain our lives would surrender their gaseous freedom and collapse into cold, colorless puddles. Liquid helium, the coldest commonly used substance in laboratories, boils at just 4.2 Kelvin. At that temperature, we are already deep into the territory where quantum mechanics dominates. Superconductivity has been discovered. The first hints of superfluidity are appearing. The classical world of Newtonian physics is giving way to the strange, probabilistic landscape of quantum behavior. And then there is the cosmic microwave background, sitting at 2.725 Kelvin, almost at the bottom of the scale, almost at the absolute limit. The entire observable universe, in the vast spaces between stars and galaxies, hovers at roughly that temperature, a temperature so close to zero that the atoms of interstellar gas are barely twitching. The hydrogen molecules that drift between the stars are moving at roughly 200 meters per second at this temperature, still significant by human standards but glacial compared to the 500 meters per second of air molecules at room temperature. In the deepest voids between galaxy clusters, where the density of matter drops to roughly 1 atom per cubic meter, these sluggish particles drift through an emptiness so complete that they may travel for years without encountering another atom. But barely is not the same as not at all. And the distance between 2.7 Kelvin and 0 Kelvin contains some of the strangest physics the universe has to offer. Because it is in that narrow gap, in that tiny remaining fraction of thermal motion, that matter starts to behave in ways that challenge everything we think we know about physical reality. Scientists have pushed into that gap with extraordinary determination. In laboratories around the world, physicists use laser cooling to slow atoms to a fraction of a degree above absolute zero. The technique works by firing carefully tuned laser beams at a cloud of atoms from multiple directions. When an atom moves toward a laser beam, the photons it absorbs give it a tiny kick in the opposite direction, slowing it down. Do this from all 6 directions: up, down, left, right, forward, back, and you create what physicists call optical molasses. The atoms are trapped in a web of light, their motion sapped by the relentless pressure of photons. After laser cooling, scientists use a second technique called evaporative cooling, which works on the same principle as a hot cup of coffee losing steam. They allow the most energetic atoms to escape the trap, carrying their extra energy with them. The remaining atoms, now lacking their hottest members, settle into an even lower average temperature. The elegance of laser cooling lies in a subtle trick of quantum mechanics. The lasers are tuned to a frequency slightly below the natural absorption frequency of the atom. Because of the Doppler effect, an atom moving toward a laser beam sees the light shifted to a slightly higher frequency, which brings it into perfect resonance with the atom's absorption line. The atom absorbs the photon and receives a momentum kick in the direction opposite to its motion. An atom moving away from the same beam sees the light shifted to an even lower frequency, further out of resonance, and is much less likely to absorb. The result is a selective braking force. Atoms moving toward any of the beams are slowed. Atoms moving away are mostly ignored. The net effect is that the average speed of the atoms in the trap decreases steadily with time. This technique earned its inventors, Claude Cohen-Tanuji, Stephen Chu, and William Phillips, the 1997 Nobel Prize in Physics, and it opened the door to an entire new branch of science. Ultra-cold physics, the study of matter at temperatures below a millionth of a Kelvin, has produced discoveries that would have seemed like science fiction a generation ago. In 2018, NASA launched the Cold Atom Lab aboard the International Space Station. This instrument was specifically designed to create Bose Einstein condensates in the microgravity environment of orbit. On Earth, gravity pulls the ultra-cold atoms downward, limiting the time scientists can observe them in their quantum state. But in the weightlessness of the ISS, the atoms float freely, allowing much longer observation times and potentially much lower temperatures. The Cold Atom Lab has projected that it could achieve temperatures as low as 1 picokelvin, 1 trillionth of a degree above absolute zero. At that temperature, the quantum wave functions of the atoms would extend to macroscopic scales, potentially visible to the naked eye. Quantum mechanics, the theory of the very small, would manifest at the scale of the very large. Using these methods, researchers have cooled matter to breathtaking extremes. In 2021, a team at the University of Bremen achieved a temperature of 38 picokelvin, that is 38 trillionths of a degree above absolute zero. At that temperature, atoms are moving so slowly that their behavior is dominated entirely by quantum mechanics. They are no longer acting as individual particles in the classical sense. They are something else entirely, something that only exists in the whisper range of the Kelvin scale. And it is there, in that whisper range, that one of the most remarkable predictions in the history of physics was finally confirmed. A prediction made in 1924, not by experiment, but by pure mathematical reasoning, by two men whose collaboration would reshape our understanding of matter itself. But before we go to the laboratory, we need to go somewhere far more dramatic. 5,000 light years from Earth, in the constellation Centaurus, there is a dying star surrounded by a cloud of gas so cold that it absorbs the background radiation of the universe itself. It is the coldest natural place ever found. Colder than the faint glow of the Big Bang, colder than the void between galaxies. And the story of how it got that way is one of the most fascinating puzzles in all of astrophysics. It is called the Boomerang Nebula, although its true shape is nothing like a boomerang. When astronomers Keith Taylor and Mike Scarrett first observed it in 1980, using a ground-based telescope in Australia, they could only make out a slight asymmetry in the cloud, a vague curve that reminded them of a boomerang. The name stuck, even after later observations revealed something far more dramatic. When the Hubble Space Telescope trained its eye on the nebula, it showed two opposing lobes of gas billowing out from a central star, forming the shape of a bow tie. The Hubble image was exposed for 1,000 seconds through a green-yellow filter, and the light it captured was not emitted by the gas itself. It was starlight from the central star, reflected by dust particles in the lobes. The nebula was glowing with borrowed light, the dying star illuminating its own funeral shroud. And when the Atacama Large Millimeter Array, ALMA, mapped the nebula in 2013, it revealed an even more ghostly form, a round, patchy cloud surrounding an hourglass of molecular gas and dust, like a phantom draped in the light of a dying star. The ALMA observations were revolutionary because they could see what Hubble could not. The cold molecular gas that fills the outer regions of the nebula is invisible in optical light. It does not glow. It does not reflect. It exists only as a faint signal in the millimeter wavelengths of the radio spectrum, detectable only by the most sensitive radio telescopes on Earth. What ALMA revealed was that the bow tie shape seen by Hubble was just the illuminated inner core of a much larger, rounder structure. The true Boomerang Nebula is not a bow tie at all. It is closer to a ghostly sphere, within which the hourglass-shaped inner nebula sits like an hourglass inside a snow globe. The ALMA team, led by Sahai, found that millimeter-scale dust grains in the nebula waste were obscuring portions of the central star's light. These grains, far larger than typical interstellar dust, created a mask that blocked the starlight and allowed it to leak out only in narrow opposing directions. This selective illumination created the bow tie appearance in optical images. Without ALMA's ability to peer through the dust at radio wavelengths, the true shape and extent of the nebula would have remained hidden. At the center of this structure is a star in its death throes. Once, it was likely much like our own sun, a stable middle-aged star fusing hydrogen in its core. But it has moved beyond that stage. It has swelled into a red giant and begun shedding its outer layers in the violent last chapters of stellar evolution. This is a process that happens to many stars of similar mass. As their cores contract and their outer atmospheres expand, they release tremendous amounts of material into space, creating what astronomers call a planetary nebula, a misleading name since it has nothing to do with planets. What makes the Boomerang Nebula different from every other planetary nebula is the sheer violence of its outflow. The central star has been losing mass at a staggering rate, roughly 1,000th of a solar mass every year, for at least the last 1,500 years. That is 10 to 100 times more than what is typically seen in similar dying stars. And the gas is not merely drifting outward. It is being blasted away at 164 kilometers per second, roughly 500,000 kilometers per hour. A wind of molecules screaming into the void at a speed that dwarfs anything else observed in this class of object. The leading theory for why this is happening involves a companion star. Scientists believe the central star is actually part of a binary system, two stars orbiting each other in close proximity. As the larger star expanded into its red giant phase, the smaller companion was drawn inward by gravity, spiraling closer and closer until it was engulfed by the outer layers of the giant star. This process, called common envelope evolution, released an enormous amount of gravitational energy. That energy was transferred to the surrounding gas, accelerating it outward with far more force than the dying star could produce on its own. The smaller star essentially dove into the heart of the larger one, and, in doing so, triggered an explosion of material into space. Raghvendra Sahai, the principal scientist at NASA's Jet Propulsion Laboratory, who has studied the boomerang more extensively than anyone, described the process vividly. The companion star spiraled inward, transferring its orbital energy to the envelope of the giant. The result was something far more energetic than a typical stellar wind. The mechanical momentum of the outflow exceeds the total radiative momentum of the central star by a factor of more than 10,000. In other words, the force pushing the gas outward is 10,000 times greater than what the star's light alone could account for. Something extra is at work, and the most plausible explanation is the gravitational energy released by the spiraling companion. The 2013 ALMA observations added another layer to the mystery. The high-resolution data revealed that the nebula is not a simple two-lobed structure. The central hourglass shape, visible in Hubble images, is surrounded by a much larger, roughly spherical cloud of cold, high-velocity gas. This outer cloud was invisible in visible light, but glowed faintly in the millimeter wavelengths that ALMA is designed to detect. The observations also found a compact source of millimeter wave continuum emission in the nebula waste, indicating the presence of unusually large dust grains, some of them millimeter-sized, in the equatorial region of the nebula. These grains may have been produced by the violent interaction between the two stars, ground out of the envelope material during the chaotic process of common envelope ejection. There is another detail about the boomerang that is easy to overlook but deeply significant. The carbon-12 to carbon-13 ratio in the nebula is unusually low, roughly 5:1, compared to the 20:1 ratio typical of the interstellar medium. This low ratio is close to the theoretical minimum achievable through equilibrium CNO cycle nucleosynthesis, the process by which stars convert carbon and nitrogen isotopes in their cores. This tells us something about the internal processes of the central star. It had undergone extensive nuclear processing, cycling its carbon through multiple rounds of fusion before ejecting the material that now forms the nebula. The cold gas surrounding the boomerang is not just cold. It is chemically distinct, carrying the fingerprints of extreme stellar evolution in its molecular composition. And this is where the cold enters the story. When a gas expands rapidly, it cools. This is not a quirk of certain gases or certain conditions. It is a universal principle of thermodynamics called adiabatic cooling. When molecules spread out into a larger volume without absorbing external heat, their kinetic energy is spent pushing against the expansion. They slow down. Their temperature drops. This is the same principle that makes the air feel cold when it rushes out of a punctured tire. It is the same principle that drives refrigerators and air conditioners. Expansion cools. You can feel this principle at work with something as simple as a can of compressed air, the kind used to clean keyboards and electronics. When you press the nozzle and release a stream of gas, the can grows cold in your hand. The gas inside was compressed and warm. As it expands into the open air, its molecules spread out and lose kinetic energy. The temperature drops sharply. If you hold the nozzle down long enough, frost will form on the outside of the can. This is adiabatic cooling at work, on a scale small enough to fit in your palm. Now imagine that same principle operating on a cosmic scale. Instead of a can of compressed air, you have a dying star ejecting its outer layers at 500,000 kilometers per hour. Instead of a few grams of propellant, you have 1,000th of a solar mass of molecular gas being flung into a void so empty that there is nothing to absorb the expansion energy. The gas spreads out, and out, and out, into a volume billions of times larger than its starting point. And with each doubling of volume, the temperature falls further. The kinetic energy of the molecules is converted into the work of expansion, and what remains is a gas colder than anything else in the natural universe. In the Boomerang Nebula, the expansion is extreme. The gas is being flung outward at such a rate and into such a vast volume that its temperature has plummeted below the background temperature of the universe. The carbon monoxide molecules in the outflow, measured by their absorption of background microwave radiation, are sitting at approximately 1 Kelvin, 1 degree above absolute zero, nearly 2 degrees colder than the cosmic microwave background that bathes the rest of the universe. This makes the Boomerang Nebula the only known natural object colder than the afterglow of the Big Bang. Think about that for a moment. The entire universe, every galaxy, every void, every patch of seemingly empty space is warmer than this one small cloud of gas surrounding a dying star. The cosmic background radiation, that ancient glow left over from the birth of everything, pours into the Boomerang Nebula from all directions. And instead of warming the gas to its temperature, the gas is so cold that it absorbs that radiation. The nebula is literally drinking in the oldest light in the universe and still remaining colder. This was confirmed in 1995 by astronomers Raghvendra Sahai and Lars Åke using the Swedish ESO submillimeter telescope in Chile. They observed that the carbon monoxide in the nebula was absorbing the background microwave radiation rather than emitting above it. This was the signature of a temperature below the background, a discovery that had been theoretically predicted but never observed in nature. The way they detected this is worth understanding, because it illustrates one of the clever methods astronomers use to measure temperatures across vast distances. Carbon monoxide molecules, like all molecules, can absorb and emit radiation at specific frequencies determined by their quantum energy levels. When a cloud of CO gas is warmer than the radiation passing through it, the molecules emit more photons than they absorb, and the cloud appears bright at those frequencies. But when the gas is colder than the background radiation, the situation reverses. The molecules absorb more than they emit, and the cloud appears as a dark shadow against the microwave background. This is exactly what Sahai and Nyman observed. The Boomerang Nebula was casting a shadow in the cosmic microwave background. It was drinking in the oldest light in the universe. No other natural object has ever been observed to do this. Every other cloud of gas, every other nebula, every other region of space that has been measured is warmer than the CMB. The Boomerang stands alone. It is a singular anomaly in a universe where the background radiation sets the thermal floor for everything else. And the fact that it exists at all, that a natural process can undercut the temperature of the oldest light in the cosmos, forces us to rethink what we mean when we say that space is cold. Space is not just cold. Space has a minimum temperature. And the Boomerang Nebula is the only known place where nature has found a way beneath it. Sahai later reflected on what drew him to the nebula. He had been thinking about the idea that somewhere in the universe there must be a place where a natural process had pushed a region below the universal temperature floor. The rapid expansion of a stellar outflow was the most likely candidate, and the Boomerang Nebula, with its extreme mass loss rate and blistering wind speed, was the perfect example. But there is an important caveat. The Boomerang Nebula will not stay this cold forever. Observations suggest that portions of the nebula are already beginning to warm as the expansion slows and the background radiation gradually reheats the gas. The ALMA observations from 2013 confirmed that while the outermost regions of the high-velocity outflow remain below the CMB temperature, some inner regions have already warmed above it. The cold is retreating inward, shrinking as the expansion loses momentum and the ancient photons of the background reassert their thermal dominance. In astronomical terms, this extreme cold is a temporary condition, a fleeting moment in the life of a dying star. The Boomerang Nebula is estimated to be only about 1,500 years into its outflow phase. In another few thousand years, as the expansion slows and the gas disperses further, the entire nebula will have warmed above the CMB temperature. It will become just another planetary nebula, glowing faintly in the light of the white dwarf that its central star will eventually become. The record for coldest natural place in the universe will pass to some other object, or perhaps to no object at all, as the background radiation maintains its gentle monopoly on the minimum temperature of the cosmos. The universe is patient. The background glow will eventually win, and the Boomerang Nebula will settle back to the same 2.7 degrees as everything else. But the fact that the record was set at all tells us something important. It tells us that the universe is not a static, uniform bath of cold. It is a dynamic place where local processes can temporarily overwhelm the global baseline. A dying star, through nothing more exotic than rapid gas expansion, can produce conditions colder than the cosmic background that has been cooling for 13.8 billion years. The coldest place in the universe was not formed in the Big Bang or in the depths of the interstellar void. It was formed by a star in the act of dying. And that is a reminder that the universe's relationship with temperature is far more complex, far more dynamic, and far more surprising than a simple number on a thermometer might suggest. For now, though, it stands as a monument to one of the most counterintuitive ideas in physics, that a dying star, in the act of violently shedding its own body, can create a pocket of cold deeper than anything the universe has produced in nearly 14 billion years of cooling. That the process of destruction can generate conditions colder than the background hum of creation itself. And the Boomerang is not alone in challenging our assumptions about cosmic temperatures. The universe is a patchwork of thermal extremes that would seem absurd if they were not measured and confirmed. Consider the surface of Venus, where a runaway greenhouse effect holds the temperature at a steady 465 degrees Celsius, hotter than the melting point of lead, hotter than many kitchen ovens, and nearly uniform across the entire planet, day and night, pole to equator. Or consider the cores of the most massive stars, where temperatures reach billions of degrees, so hot that atomic nuclei are stripped bare and fused together with violent force. Or consider the moment of the Big Bang itself, when temperatures exceeded 10 to the power of 32 Kelvin, a number so large that it makes the interior of a star look like a snowflake by comparison. The range of temperatures in the universe spans roughly 32 orders of magnitude, from the picokelvin cold of laboratory condensates to the Planck temperature, the theoretical maximum beyond which our understanding of physics breaks down entirely. And we exist on this spectrum at a very specific point. Our bodies operate at roughly 310 Kelvin. Our civilization functions in a temperature band of perhaps 50 degrees on either side of that. We are creatures of a narrow slice, a thin ribbon of thermal comfort stretched across an almost inconceivably vast scale. And here is what makes the cold end of that scale so much more interesting than the hot end. Heat creates chaos. The higher the temperature, the faster particles move. The more violently they collide, the less structure can survive. At the temperatures inside a star, atoms are stripped to their cores. At the temperatures of the early universe, matter itself could not hold together. Heat is destructive. Heat is entropy in action. But cold is the opposite. Cold creates order. Cold slows particles down, allows them to interact gently, permits structures to form that would be impossible at higher temperatures. Snowflakes are an everyday example. The intricate six-fold symmetry of an ice crystal is a product of cold. The molecules of water, freed from the chaotic jostling of the liquid state, settle into a precise geometric lattice, dictated by the angles of hydrogen bonds. Warmth would destroy that pattern. Cold creates it. And at the very lowest temperatures, the order becomes total. Matter does not just slow down. It synchronizes. Particles that were once independent fall into lockstep. Waves that were once random become coherent. The cold imposes a kind of unity on matter that has no parallel at any other temperature. And the consequences of that unity are among the strangest things ever observed in a laboratory. This brings us to a question that pushes us even deeper into the mystery. If the universe has a temperature floor, if the cosmic microwave background keeps everything at roughly 2.7 Kelvin, what happens when scientists on Earth deliberately push past that limit? What happens when we cool matter, not just to 1 degree above absolute zero, but to billions, trillions, or even quadrillions of a degree? The answer is that matter starts to do things that should be impossible. Let us start with something you can almost picture. Imagine a glass beaker sitting on a laboratory bench filled with liquid helium. At room temperature, helium is an invisible gas, the second lightest element in the universe, famous for making balloons float and voices squeak. But cool it down to 4.2 Kelvin, negative 269 degrees Celsius, and it surrenders its gaseous freedom and condenses into a liquid. Clear, colorless, and utterly unremarkable to look at. Helium is the last holdout among the elements. Every other substance in the periodic table can be frozen solid at low enough temperatures. Hydrogen freezes at 14 Kelvin, nitrogen at 63, oxygen at 54, but helium resists. Even at absolute zero at normal atmospheric pressure, helium remains a liquid. It simply refuses to solidify. The reason, as we discussed earlier, is zero-point energy. The helium atom is so light, and the attractive forces between helium atoms are so weak, that the residual quantum motion at absolute zero is enough to prevent the atoms from locking into a crystal lattice. To freeze helium solid, you need to apply roughly 25 atmospheres of pressure, physically squeezing the atoms close enough together to overcome their quantum restlessness. No other element behaves this way. Helium is unique, and its uniqueness is a direct consequence of quantum mechanics operating at macroscopic scales. Now cool it further. Below 2.17 Kelvin, something extraordinary happens. The liquid helium undergoes what physicists call a phase transition, but this is not like water turning to ice or steam turning to rain. This is a transition into a state of matter that has no equivalent in our everyday experience. The helium becomes a superfluid. The transition is dramatic and sudden. If you were watching a pot of liquid helium boiling at 4.2 Kelvin and slowly pumped away the vapor to reduce the pressure, you would see the liquid bubbling vigorously, just like boiling water. But the moment the temperature crosses 2.17 Kelvin, the lambda point, the boiling stops, instantly, completely. One moment the liquid is churning with bubbles. The next, it is perfectly still, perfectly calm, perfectly transparent. The transition is so abrupt and so visually striking that early experimenters were startled by it. The liquid had not frozen. It had not stopped being a liquid, but it had stopped behaving like any liquid they had ever seen. A superfluid has zero viscosity. That is not almost zero, not very close to zero, but mathematically, exactly zero. It flows without any friction whatsoever. If you set a cup of normal liquid spinning and walked away, the liquid would slow down and stop within seconds because the molecules collide with each other and with the walls of the cup, gradually losing energy. But if you set a cup of superfluid helium spinning and walked away, it would still be spinning when you came back. Not in a minute. Not in an hour. In a million years, it would still be rotating at exactly the same speed, because there is nothing, absolutely nothing, to slow it down. Pyotr Kapitsa, the Soviet physicist who first discovered superfluidity in 1937, was awarded the Nobel Prize in Physics for this work. But the most famous demonstration of superfluidity is something far more visual and far more unsettling than a spinning cup. Superfluid helium climbs walls. Place superfluid helium in an open beaker, and a thin film of liquid, roughly 30 nanometers thick, will begin creeping up the inner wall of the container. It coats the entire surface. It reaches the rim. It goes over the rim. It flows down the outside of the beaker. And if there is a reservoir of lower potential energy below, it will drip off the bottom of the container, one drop at a time, until it has siphoned out every last bit of superfluid from inside. No normal liquid does this. Water can climb the sides of a narrow tube through capillary action, but it cannot flow over the top and down the outside of a beaker. The superfluid does it because its zero viscosity means the thin film coating the walls can flow without any resistance at all. The van der Waals forces between the helium atoms and the glass surface pull the fluid upward, and without friction to oppose the motion, it simply keeps going, up and over, defying gravity, moving with a silent, almost eerie purpose. John Beamish, an experimental physicist at the University of Alberta, put it this way: if you set a cup with normal liquid circulating and came back 10 minutes later, it would have stopped moving. But if you did that with helium at low temperature and came back a million years later, it would still be moving. This is because the helium is no longer behaving as a collection of individual atoms. It has become something more unified, more coordinated, something quantum mechanical. The reason superfluidity occurs specifically in helium and not in other liquids has to do with the peculiar properties of helium atoms. Helium is the lightest noble gas, and its atoms are extraordinarily simple. 2 protons, 2 neutrons, 2 electrons. The electron cloud around a helium atom is so symmetric and so tightly bound that the forces between neighboring helium atoms are incredibly weak. These are van der Waals forces, the feeblest of all intermolecular attractions, and they are the reason helium remains a gas down to the lowest temperatures of any element. It is the last gas to surrender to the liquid state, and once it does, its behavior is unlike any other liquid on Earth. Below the critical temperature of 2.17 Kelvin, known as the lambda point, because the shape of the heat capacity curve at this transition resembles the Greek letter lambda, a fraction of the liquid helium enters a quantum state where the individual atoms become part of a single macroscopic wave function. This fraction grows as the temperature drops further. At 1 Kelvin, most of the liquid is superfluid, and this superfluid fraction is what gives liquid helium its impossible properties. There is another famous demonstration of superfluidity that deserves mention here. It is called the fountain effect, and it is almost as visually striking as the wall climbing. If you take a narrow glass tube, pack the bottom end with fine powder to create a filter, submerge it in a bath of superfluid helium, and then shine a small light on the powder, something spectacular happens. The light warms the powder slightly. The superfluid helium, which is extraordinarily sensitive to temperature differences, rushes toward the warmer region to equalize the temperature. But the powder filter allows the superfluid component to pass through while blocking the normal component. The result is a buildup of superfluid on the warm side that has nowhere to go, but up. A jet of liquid helium shoots vertically out of the open top of the tube, creating a miniature fountain that defies every intuition about how liquids should behave. The physicist Jack Allen, who co-discovered superfluidity, reportedly stumbled upon this effect accidentally when he shined a pocket flashlight onto a tube of liquid helium and watched in astonishment as the liquid erupted upward. These phenomena, the wall climbing, the perpetual circulation, the fountain effect, are not tricks or illusions. They are macroscopic manifestations of quantum mechanics. They are the visible, tangible, naked eye consequences of atoms behaving as a single unified quantum system, rather than as a collection of independent particles. And they occur because of one specific property that connects superfluid helium to the next, an even more remarkable state of matter we need to discuss. The connection is Bose Einstein condensation. Superfluidity in helium is believed to arise, at least in part, from the fact that helium-4 atoms are bosons, particles with integer spin that obey Bose Einstein statistics rather than the Fermi-Dirac statistics that govern electrons and protons. Bosons have a special property that fermions do not share. There is no limit to the number of bosons that can occupy the same quantum state at the same time. Fermions are exclusive. They obey the Pauli exclusion principle, which demands that no two fermions occupy exactly the same state. This is why electrons arrange themselves in distinct energy levels around an atom, why the periodic table has its structure, and ultimately why solid objects feel solid. But bosons are the opposite. They are gregarious. They prefer to be in the same state. They clump, and at sufficiently low temperatures, this preference becomes absolute. This is the bridge to one of the most remarkable states of matter ever observed. Because superfluidity in helium is closely related to a phenomenon predicted in 1924 by two physicists working on opposite sides of the world, and not confirmed in a laboratory until 71 years later. In 1924, an Indian physicist named Satyendra Nath Bose wrote a letter to Albert Einstein. Bose had been working on a new way to derive Planck's law of radiation, the equation that describes how objects emit light based on their temperature. His approach was radical. Instead of treating particles as distinguishable individuals, each with their own identity and trajectory, he treated them as identical and interchangeable. He essentially argued that at a fundamental level, certain particles are not individuals at all. They are more like identical drops in an ocean, and counting them requires a completely different kind of mathematics. Einstein recognized the importance immediately. He translated Bose's paper from English to German and submitted it for publication. Then he took the idea further. He applied Bose's statistical framework not just to photons, particles of light, but to atoms of matter, and he made a stunning prediction. At sufficiently low temperatures, he said, the atoms of a gas would stop behaving as separate particles. Their quantum wave functions would expand, overlap, and merge. The individual atoms would lose their identity entirely and collapse into a single quantum state. They would become, in effect, one giant superatom. Einstein predicted that this would happen when the temperature was so low that the de Broglie wavelength of each atom, the quantum mechanical wave associated with its motion, grew large enough to overlap with the high wavelengths of its neighbors. At room temperature, this wavelength is vanishingly small, far smaller than the distance between atoms. But as the temperature drops toward absolute zero, the wavelength stretches. The atom becomes less like a tiny billiard ball and more like a blurry, spread-out wave. Cool a gas enough, and those waves start to touch. Then they start to merge. And when they fully overlap, something astonishing happens. To understand why this matters, think about what a de Broglie wavelength actually represents. In 1924, the same year that Bose wrote his letter to Einstein, a French physicist named Louis de Broglie proposed that all matter has wave-like properties. Every particle, every atom, every molecule has an associated wavelength that depends on how fast it is moving. The faster the particle, the shorter the wavelength. The slower the particle, the longer the wavelength. At the speeds that atoms move at room temperature, their wavelengths are incredibly tiny, far smaller than the atoms themselves. The wave nature of the particle is essentially invisible. But as you cool the atoms and their velocities drop towards zero, their wavelengths grow, they expand, they puff out like inflating balloons of probability. And when the wavelengths of neighboring atoms grow large enough to overlap, the atoms can no longer be treated as separate objects. Quantum mechanics takes over. This is not a gradual transition. It is a phase change, as sharp and dramatic as water freezing into ice. Below a critical temperature, the atoms suddenly snap into the same quantum state. Above that temperature, they are individuals. Below it, they are one. The atoms are no longer distinguishable. You cannot tell one from another. They occupy the same quantum state, the same energy level, the same position in the language of quantum mechanics. They are not merely similar. They are identical in the deepest sense that physics allows. A collection of thousands or millions of atoms, each one indistinguishable from the next, all behaving as a single coherent entity. This state of matter is called a Bose Einstein condensate, and for 70 years it existed only as a prediction on paper. The technology to cool atoms to the required temperatures simply did not exist. But in 1995, two physicists at a laboratory in Boulder, Colorado, finally made it real. Eric Cornell of the National Institute of Standards and Technology and Carl Wieman of the University of Colorado led a team that cooled a gas of rubidium atoms to approximately 170 billionths of a degree above absolute zero. At that temperature, roughly 2,000 atoms collapsed into a single quantum state, forming a tiny ball of condensate about 20 microns across, roughly 1/5 the thickness of a sheet of paper. They had created the fifth state of matter, predicted 7 decades earlier, confirmed at last in the coldest conditions ever produced on Earth at that time. The process of making that condensate was a masterwork of precision physics. The team began with a small glass cell, about the size of a carrot, containing rubidium vapor. They used 6 intersecting laser beams to cool and trap the atoms, creating a cloud of roughly 10 million atoms at about 10 millionths of a degree above absolute zero. This was still far too hot for condensation. So they transferred the atoms to a magnetic trap and began the process of evaporative cooling, selectively allowing the hottest atoms to escape. Each departing atom carried away more than its share of energy, lowering the average temperature of those that remained. It is the same principle by which your body cools when sweat evaporates from your skin. The most energetic water molecules leave, and the remaining liquid is cooler. The trickiest part, as Wieman later described, was maintaining a high enough density of atoms at a cold enough temperature. If the cloud was too thin, the atoms would not interact enough to reach thermal equilibrium. If it was too dense, collisions between atoms would heat the sample back up. The team had to thread a needle of density and temperature, holding millions of atoms in a magnetic bottle at billionths of a degree above zero, long enough for the quantum transition to occur. And then, on June 5th, 1995, it happened. The velocity distribution of the atoms, measured by releasing them from the trap and photographing their expansion, showed a sharp spike at zero velocity, a peak of atoms that were not moving at all, or rather, that were all moving in exactly the same way, occupying exactly the same quantum state. The fuzzy ball had appeared. The superatom was real. Later that same year, Wolfgang Ketterl at the Massachusetts Institute of Technology independently created a Bose Einstein condensate using sodium atoms. Ketterle's condensate was larger, containing more atoms, and his team was able to demonstrate interference between two separate condensates, proving that the atoms were indeed behaving as coherent matter waves, analogous to the coherent light waves produced by a laser. The three scientists shared the 2001 Nobel Prize in Physics, and the field of ultra-cold physics was born. What makes a Bose Einstein condensate so remarkable is not just that it exists, but what it reveals about the nature of reality at extreme cold. When you try to measure where the atoms in a condensate are located, you do not see discrete particles. You see a fuzzy ball. The individual atoms have lost their boundaries. They are no longer separate things occupying separate spaces. They are a single quantum object, a matter wave oscillating in unison. This is where the word terrifying in our title starts to earn its keep, because at these temperatures, the familiar rules of the physical world break down. Individuality disappears. The Pauli exclusion principle, the rule that says no two electrons can occupy the same quantum state at the same time, and which is responsible for the fact that solid objects do not pass through each other, does not apply to bosons, the class of particles that form condensates. These particles can and do pile into the same state, overlapping in ways that no ordinary matter ever could. In a Bose Einstein condensate, matter is no longer a collection of separate objects. It is a chorus singing the same note, a wave front moving in perfect lockstep. If you could shrink yourself down to the atomic scale inside a condensate, you would not be able to point to any single atom and say, that is a separate thing. There would be no separate things, only the wave. Physicists have used condensates to slow light to extraordinary crawls. In 1999, Lene Howe at Harvard University fired a pulse of light into a Bose Einstein condensate of sodium atoms and slowed it from its usual 300 million meters per second to just 17 meters per second. Slower than a bicycle. The light was not being absorbed or reflected. It was being slowed, its energy temporarily stored in the coherent quantum wave of the condensate. When the pulse emerged from the other side, it resumed its normal speed, as if nothing had happened. But for a brief moment, light itself had been brought nearly to a standstill by the sheer quantum strangeness of ultra-cold matter. To appreciate how remarkable this is, consider what light does everywhere else in the universe. It is the fastest thing that exists. Nothing with mass can ever reach the speed of light. It crosses the entire solar system in a matter of hours. It spans galaxies in hundreds, of thousands of years. It is the universal speed limit, the cosmic constant around which Einstein built his theory of relativity. And in a tiny cloud of atoms cooled to near absolute zero, it was reduced to the pace of a jogger. In 2001, Howe's team went even further. They brought a light pulse to a complete stop inside a condensate, held it there for a fraction of a second, and then released it. The information carried by the light pulse was imprinted on the quantum state of the atoms, stored as a pattern in the matter wave, and then reconverted back into light on demand. It was a demonstration of something that borders on alchemy, the conversion of light into matter and back into light again. The boundary between the two most fundamental categories of physics, matter and radiation, had been blurred by cold. In 2001, the same team that created the first condensate at Boulder made another startling discovery. Under certain conditions, a Bose Einstein condensate can be made to collapse, and when it does, it explodes in a tiny burst of particles that physicists nicknamed a bosonova, a play on the word supernova. About half the atoms in the condensate vanished during the process, their fate still not fully understood. It was as though the matter, pushed to the edge of quantum coherence, had briefly decided to stop existing. And there is yet another phenomenon that emerges from the extreme cold, one that has already transformed modern technology. Superconductivity. When certain materials are cooled below a critical temperature, their electrical resistance drops to exactly zero. Not approximately zero, not very nearly zero, exactly zero. An electric current, set flowing in a superconducting loop, will circulate forever without any loss of energy. No battery needed, no external power source. The current simply flows indefinitely because there is nothing to oppose it. Superconductivity was first discovered by Heike Kamerlingh Onnes in 1911, just 3 years after he first liquefied helium. He was measuring the resistance of mercury at liquid helium temperatures and found that at 4.2 Kelvin, the resistance abruptly vanished. It did not gradually decrease. It did not approach zero asymptotically. It dropped to zero in a sudden, sharp transition. Onnes described it as a new state of the metal, fundamentally different from its normal conducting state. The mechanism behind superconductivity was not understood until 1957, when John Bardeen, Leon Cooper, and John Robert Schrieffer published their theory, now known as BCS theory. They showed that at low temperatures, electrons in a metal can form pairs, called Cooper pairs, by exchanging vibrations of the crystal lattice. These paired electrons behave as bosons rather than fermions, and like the atoms in a Bose Einstein condensate, they can all occupy the same quantum state. The superconducting current is a river of Cooper pairs flowing in quantum lockstep, perfectly coherent, perfectly coordinated, without any of the collisions and scattering events that create resistance in a normal conductor. Today, superconductors are used in MRI machines, particle accelerators, quantum computers, and the powerful magnets that will one day drive fusion reactors. All of these technologies are children of the cold. They exist because someone cooled a piece of metal below a few degrees Kelvin and discovered that the rules of electricity had changed. These are not abstract theoretical curiosities. They are observed phenomena, captured on camera, measured with instruments, replicated in laboratories around the world. They are the real consequences of pushing matter to the extreme lower boundary of the temperature scale. And they hint at something deeply unsettling about the relationship between warmth and identity. In our everyday world, objects are separate. You are you. The chair is the chair. The air between you is the air. But this separateness is not fundamental. It is a consequence of temperature, of motion, of thermal energy keeping atoms distinct and individualistic. Strip that energy away, and the distinctions begin to dissolve. This is the terrifying truth that the title promises. Not that space will freeze you, not that the cold is dangerous in the way a blizzard is dangerous, but that cold, real cold, absolute cold, erodes the very concept of individuality. At the bottom of the temperature scale, matter does not just slow down. It loses itself. Particles that were once separate merge into a single entity. Objects that were once distinct become indistinguishable. The boundaries between things, the boundaries that make the physical world feel solid and real and structured, are maintained by heat. They are sustained by motion. They are artifacts of thermal energy, and the universe is getting colder. That simple fact, stated plainly, carries more weight than almost any other statement in cosmology. The universe is expanding. It has been expanding since the Big Bang, and the expansion is accelerating. As it expands, the temperature drops. The cosmic microwave background, that 2.725 Kelvin afterglow, was once 3000 Kelvin. It has been cooling for 13.8 billion years, and it will continue to cool for trillions upon trillions of years to come. The background temperature of the universe is falling, slowly, inexorably, toward that forbidden limit at the bottom of the Kelvin scale. The acceleration of the expansion adds a particularly unsettling dimension to this cooling. In 1998, two independent teams of astronomers studying distant supernovae to measure the rate of cosmic expansion made a discovery that overturned decades of cosmological assumption. They found that the expansion of the universe is not slowing down, as gravity would predict. It is speeding up. Something is pushing the universe apart faster and faster, counteracting gravity on the larger scales. This mysterious force was given the name dark energy, and despite more than 2 decades of investigation, we still do not know what it is. We know only that it constitutes roughly 68% of the total energy content of the universe, and that it is driving the expansion to accelerate exponentially. The implications for the temperature of the cosmos are profound. In a universe expanding at a constant rate, the CMB would cool gradually, approaching absolute zero over infinite time. But in a universe with accelerating expansion, the cooling is faster. The photons of the microwave background are being stretched more rapidly. The distances between galaxy clusters are growing at an ever-increasing pace. And the final temperature of the universe, the asymptotic limit it approaches in the infinite future, may be even colder than what a simple constant expansion would produce. Some models suggest that the de Sitter temperature, the minimum temperature of an exponentially expanding universe dominated by dark energy, is on the order of 10 to the power of negative 30 Kelvin, a number so close to absolute zero that it is, for all practical purposes, indistinguishable from it. And this leads us to the largest and most sobering question of all. What happens at the end? What does the universe look like when the cold finally wins? To answer this, we need to confront a concept that lies at the very heart of physics and philosophy alike: the arrow of time. In our everyday experience, time moves in one direction. Eggs break but do not unbreak. Ice melts but does not spontaneously freeze in a warm room. Stars burn but do not unburn. This asymmetry, so obvious and so pervasive that we barely think about it, is a direct consequence of the second law of thermodynamics. Entropy increases. Disorder spreads. Concentrated energy disperses into diffuse energy, and the direction of that dispersal defines the direction of time. Every irreversible process in the universe. Every chemical reaction, every mechanical friction, every biological metabolism produces entropy. And entropy, once produced, cannot be destroyed. It can be moved from one place to another, which is what refrigerators do. But the total entropy of the universe, summing up every particle and every field and every photon, can only increase. It is a one-way ratchet. Click by click, the universe moves from order to disorder, from concentrated to diffuse, from hot to cold. The heat death is simply what happens when the ratchet reaches its final click. When entropy is at its maximum, when there are no more temperature gradients to exploit, no more energy differences to tap, no more order to consume, the universe will not end in fire or ice in the traditional poetic sense. It will end in sameness, in the perfect, featureless, unchanging uniformity of a system that has exhausted every possible thermodynamic transaction. But before we reach the end of everything, there is one more phenomenon from the cold that deserves our attention. Something that happens not in the depths of space or the chill of a laboratory, but in the practical mechanical world of spacecraft engineering. Something that sounds almost impossible until you understand the physics, and it has caused real failures on real missions. In the vacuum of space, if two pieces of clean metal of the same type are brought into contact, they will bond together, instantly, permanently, without heat, without pressure, without any welding equipment. The two separate pieces become one. This is called cold welding, and it happens because of something remarkably simple. On Earth, every metal surface is coated with a thin layer of oxide. When iron is exposed to oxygen, it forms iron oxide or rust. When aluminum meets air, it forms a microscopic layer of aluminum oxide that is invisible to the naked eye, but serves as a barrier between the pure metal beneath and the outside world. This oxide layer, along with traces of grease, moisture, and other contaminants, is what keeps metals from bonding to each other spontaneously. The atoms on the surface of one piece of aluminum never actually touch the atoms on the surface of another piece, because there is always something in between. The phenomenon was first recognized in the 1940s, when scientists conducting experiments in the vacuum chambers noticed that freshly cleaned metal surfaces would stick together with surprising force. The effect puzzled researchers for years until the atomic scale explanation became clear. Try Earth, the oxide layer reforms almost instantly whenever a metal surface is exposed to air. You can scrub it away, but within milliseconds, a new layer forms. The oxygen in our atmosphere is like a constant invisible shield that prevents metals from making direct atomic contact. We take this shield for granted because it is always there. In the vacuum of space, those barriers vanish. There is no oxygen to form new oxide. The existing oxide can be worn away by friction or vibration. And once two clean metal surfaces are in direct contact, the atoms on one surface cannot distinguish themselves from the atoms on the other. They are the same element, in the same arrangement, with the same electron configuration. From the perspective of the atoms, there is no boundary, there is no reason not to bond. And so they do. The metallic bonds that hold the atoms together within each piece extend across the interface, fusing the two surfaces into a single continuous structure. Richard Feynman, one of the greatest physicists of the 20th century, described the phenomenon in his famous lectures. He said that when the atoms in contact are all of the same kind, there is no way for the atoms to know that they are in different pieces of copper. When there are other atoms, in the oxides and greases and surface layers of contaminants in between, The atoms know when they are not on the same path. This is not merely a laboratory curiosity. In 1991, NASA's Galileo spacecraft, on its way to study Jupiter, encountered a critical failure when its high-gain antenna refused to fully deploy. Investigation revealed that 3 of the antenna's umbrella-shaped ribs had cold welded together during transport and launch. The vibrations of the rocket had worn away the protective coatings on the metal contact points, exposing bare surfaces. In the vacuum of space, those surfaces bonded. The antenna was permanently stuck, and the mission was forced to rely on a much smaller, much slower low-gain antenna for the remainder of its journey. The consequences for the mission were severe. The high-gain antenna had been designed to transmit data back to Earth at 134 kilobits per second. The low-gain antenna could manage only about 10 bits per second. That is not a typo. 10 bits per second. The difference is roughly equivalent to going from a broadband internet connection to communicating by Morse code. NASA engineers spent years developing data compression techniques and modifying the deep space network to squeeze as much science as possible through that tiny data pipe. The Galileo mission ultimately produced extraordinary results, including evidence of a subsurface ocean on Europa and detailed observations of Jupiter's atmosphere. But it did so despite the crippling handicap imposed by 3 tiny patches of bare metal that had fused together in the void. The Galileo failure became a textbook example in aerospace engineering. Cold welding is now recognized as a significant engineering challenge for any spacecraft with moving metal parts. Engineers combat it with careful selection of dissimilar metals at contact points, specialized coatings that resist wear, and solid lubricants like molybdenum disulfide that maintain a barrier between surfaces even in vacuum. Every hinge, every latch, every deployable mechanism on a modern satellite is designed with this phenomenon in mind. The European Space Agency has published extensive guidelines for testing material combinations against cold welding, and aerospace companies maintain databases of which metal pairings are safe and which are dangerous. It is a constant, invisible battle against the universe's tendency to erase the boundaries between objects when those boundaries are no longer maintained by chemistry. And there is something philosophically striking about cold welding that connects back to our earlier discussion of Bose Einstein condensates. In both cases, the removal of barriers leads to a loss of individuality. In a condensate, atoms lose their quantum distinctness when thermal energy is stripped away. In cold welding, metal parts lose their mechanical distinctness when the chemical barriers of oxide and contamination are stripped away. The pattern repeats across scales and across phenomena. Identity, separateness, the quality of being a distinct thing, is not inherent to matter. It is maintained by energy, by motion, by the thin layers of complexity that heat and chemistry provide. Remove those layers, strip away the barriers, and things merge. Boundaries dissolve. Individuality is not a fundamental property of the universe. It is a thermal luxury. Consider what this means at a deeper level. The chair you are sitting on feels solid. It feels like a distinct object, separate from the floor beneath it and the air around it. But that distinctness is maintained by the electromagnetic forces between atoms on its surface and the atoms of whatever it touches. Those forces, in turn, are shaped by the electron configurations of the surface atoms, which are influenced by temperature, by oxide layers, by the presence of contaminants and absorbed molecules. The chair is a distinct object because the conditions at its surface maintain a barrier between its atoms and the atoms of its surroundings. Change those conditions, strip away the oxide, remove the air, lower the temperature, and the boundary between the chair and the floor would begin to blur. At room temperature in an atmosphere, this is impossible. At absolute zero in a vacuum, it is inevitable. The same principle applies to you. The boundary between your body and the rest of the universe is maintained by chemistry, by the membranes of your cells, by the electrical signals in your nerves, by the constant metabolic activity that keeps your tissues organized and your surfaces distinct. All of this requires energy. All of this requires heat. Cool your body to absolute zero, and those boundaries would not just weaken. They would cease to have meaning. The atoms that make up your body would be indistinguishable from the atoms of the environment. You would not just be dead. You would be gone, in the deepest physical sense. Not destroyed, but dissolved. Merged with the background. Return to the undifferentiated quantum state from which all matter emerges. This is one of the deepest insights that the study of cold has to offer, and it is worth sitting with for a moment. Everything you see around you, every object that appears solid and permanent and separate from every other object, is only that way because of warmth, because of the restless jittering of atoms that keeps surfaces contaminated, keeps electrons in their individual orbitals, keeps the quantum wave functions of neighboring particles from overlapping. Turn down the temperature, and the walls between things begin to thin. Turn it down far enough, and the walls disappear entirely. Consider what this means on the most fundamental level. The chair you are sitting in feels solid because the electrons in its atoms are repelling the electrons in the atoms of your body. Those electrons occupy distinct energy levels, distinct orbitals, distinct quantum states. They are individualized by the thermal energy that keeps them jittering in their assigned positions. But at absolute zero, or near it, the rules change. The bosonic particles that make up certain types of matter can collapse into shared quantum states. The fermions, electrons and protons, can pair up into Cooper pairs and behave collectively. The boundaries between separate quantum states blur. The hard edges of the physical world, the surfaces and membranes that keep one thing from being another thing, are all maintained by the same underlying phenomenon: thermal energy. The philosopher might call this a deeply unsettling realization. The physicist might call it the most beautiful, because it means that the separateness we experience in everyday life, the feeling of being a distinct object in a world of distinct objects, is not a fundamental feature of reality. It is an emergent property of temperature. It is a consequence of living in the warm zone of the Kelvin scale. At the bottom of that scale, separateness dissolves. Identity merges. The universe is not fundamentally made of separate things. It is fundamentally made of overlapping waves. And it is only because we live in a warm pocket of the cosmos, bathed in the radiation of a nearby star, that those waves are jostled and scattered into the experience of distinct individual objects. We are warm enough to be individuals. That is a privilege, and then it is a temporary one. The universe knows this. The universe has always known this, in the sense that its laws encode this truth at the deepest level. The trend toward equilibrium, toward uniformity, toward the dissolution of differences, is built into the fabric of thermodynamics. Every cup of coffee that cools, every star that burns out, every warm body that radiates its heat into the void, is a small step along a cosmic path that leads, ultimately, to a state in which nothing is warmer than anything else. A state in which all the boundaries maintained by thermal energy have dissolved. A state of perfect, featureless sameness. We are walking that path right now. Every second, the universe takes another step. Now, let us turn the temperature down on the universe itself. The story of the universe's future is a story of cooling. It always has been. From the incandescent fury of the Big Bang, when temperatures exceeded trillions of degrees, to the relatively mild warmth of the present era, when stars burn steadily and planets orbit comfortably around them, the arc of cosmic history bends toward cold, and the trajectory does not reverse. The universe will not heat up again. The expansion will continue, the temperature will fall, and the consequences will unfold over timescales so vast that human numbers struggle to contain them. Before the deep future arrives, though, there is one more act of cosmic theatre to play out in our own neighborhood. In roughly 4.5 billion years, the Milky Way galaxy will collide with the Andromeda Galaxy, our nearest large galactic neighbor. The two spiral galaxies are currently approaching each other at about 110 kilometers per second, drawn together by their mutual gravitational attraction. When they meet, the collision will not be the violent smash-up that the word collision implies. The distances between individual stars are so vast that almost no stars will physically touch, but the gravitational interaction will be profound. Stars will be flung from their orbits. Gas clouds will collide and compress, triggering a burst of new star formation. The elegant spiral structures of both galaxies will be destroyed, replaced over hundreds of millions of years by a single, massive elliptical galaxy that astronomers have already nicknamed Milkdromeda. Our Sun, if it is still burning at that point, will find itself in a completely different galactic environment, orbiting a new center of gravity in a galaxy that no longer resembles the one we call home. This merger will produce one last great burst of starlight, one last flare of warmth before the long descent begins, and then the newly combined galaxy will begin the slow process of using up its remaining gas, forming its final generation of stars and settling into the eternal quiet. We live in what astronomers call the stelliferous era, the age of stars. It began a few 100 million years after the Big Bang, when the first clouds of hydrogen and helium collapsed under their own gravity and ignited nuclear fusion. For the last 13.8 billion years, the universe has been full of stars. They light up galaxies, they warm planets, they forge the heavy elements that make up our bodies: carbon in our bones, iron in our blood, oxygen in our lungs, all of it cooked in the nuclear furnaces of stars that lived and died before our Sun was born. The first generation of stars, known to astronomers as Population 3, were enormous. Without heavy elements to help clouds cool and fragment, the first collapsing gas clouds produced monsters, stars hundreds of times the mass of our Sun, burning at ferocious temperatures and dying within a few million years in cataclysmic supernovae. Those explosions seeded the surrounding gas with the first heavy elements: carbon, oxygen, silicon, iron, enriching the raw material from which the next generation of stars would form. Each successive generation contained more heavy elements than the last, a process astronomers call chemical enrichment. Our Sun is a third-generation star, born from gas that had been processed through at least 2 previous cycles of stellar life and death. The calcium in your teeth was forged in the heart of a star that died before the Sun existed. The gold in a ring was produced in the collision of 2 neutron stars, an event so violent that it briefly outshone an entire galaxy. But the stelliferous era is not permanent. It is a chapter, not the whole book, and it is a chapter that is already closer to its end than its beginning. Star formation requires raw material. Vast clouds of hydrogen and helium cold and dense enough to collapse under gravity. In the early universe, these clouds were everywhere. The cosmos was rich with the raw fuel of stellar birth. But every time a star forms, it consumes some of that fuel. The hydrogen is fused into helium, the helium into carbon, the carbon into oxygen, and on through the periodic table until iron fills the core, and the star can fuse no more. Some of that material is recycled when the star dies, blown back into space by supernovae, or shed in planetary nebulae like the Boomerang. But not all of it. With each generation of stars, a little more of the available gas is locked away in stellar remnants, white dwarfs, neutron stars, and black holes that do not return their substance to the interstellar medium. The process is something like a bank account with no new deposits. Each withdrawal, each new star born, draws down the balance. And while some stars return a portion of their mass to the cosmic account when they die, the return is never 100%. A fraction is always retained. Slowly, generation by generation, the balance shrinks. The universe is spending its inheritance of hydrogen, and there is no cosmic employer to replenish the fund. The evidence for this decline is already visible. Astronomers studying galaxy surveys, including a major project called the Galaxy and Mass Assembly Survey, have found that the total energy output of the local universe has dropped by roughly half over the last 2 billion years. The universe is already fading. The peak era of star formation occurred roughly 10 billion years ago, and we are living in the long, slow twilight that follows. The universe is slowly running out of gas. Star formation has already peaked. It was at its most vigorous roughly 10 billion years ago, and it has been declining ever since. In about 1 to 100 trillion years, depending on the precise rate of decline, the last star will form, and not long after that, the last star will die. The final generation of stars will be the smallest ones, red dwarfs, faint, cool, miserly with their fuel, burning so slowly that they can shine for trillions of years. The largest, brightest stars live fast and die young, burning through their hydrogen in mere millions of years. A star like Betelgeuse, the red supergiant that marks the shoulder of Orion, has a mass roughly 20 times that of our Sun and will exhaust its fuel in roughly 10 million years. Compare that to our Sun, which will burn for roughly 10 billion years total, or to a small red dwarf like Proxima Centauri, our nearest stellar neighbor, which will quietly fuse hydrogen for perhaps 4 trillion years. The universe is currently 13.8 billion years old. Proxima Centauri has used less than 1% of its total fuel supply. It will still be shining long after every massive star in the galaxy has died and been forgotten. But even the most patient red dwarf has a limit. In 10 trillion years, give or take, even the longest-lived stars will have consumed their hydrogen and begun to cool. They will contract, their cores no longer producing the outward pressure needed to balance the inward pull of gravity. Their surfaces will dim from red to brown to black, and one by one, across the entire observable universe, the lights will go out. There is something uniquely poignant about the death of the last star. Not because it will be dramatic. It will not. The last star will likely be a small, feeble red dwarf in some unremarkable corner of a galaxy that has long since gone dark. Its death will be quiet, a gradual fading, a slow dimming, a gentle descent into permanent night. No one will witness it, because by that point, any civilization that ever existed will have been gone for trillions of years. The last star will die alone, and its death will mark the end of a cosmic era that lasted far longer than all of recorded history. all of human evolution, all of the time since the first complex life appeared on Earth. When the last red dwarf exhausts its hydrogen and cools to a brown, lightless cinder, the stelliferous era will end. The universe will go dark. Not the temporary darkness of a cloudy night, but a permanent, irreversible darkness. No new stars will form. No new light will be generated. The cosmos will enter a long, quiet period that astronomers call the degenerate era, a name that reflects the state of the matter that remains, not a moral judgment. In the degenerate era, the universe will be populated by the corpses of stars. White dwarfs, the dense, Earth-sized remnants of mid-sized stars like our Sun, will slowly radiate away their stored thermal energy over trillions of years, cooling from white to yellow to red to brown to black. They will become black dwarfs, objects so cold and dim that they emit no detectable radiation at all. No black dwarf has ever been observed, because the universe is not yet old enough for one to have formed. The youngest white dwarfs, the ones created by the first generation of sun, like stars to die, are still cooling. They still glow. The universe has not had enough time to make even one completely dark stellar corpse, but in the degenerate era, the cosmos will be filled with them. Trillions upon trillions of cold, dark, dead stars drifting through an equally dark and empty universe. Neutron stars, the ultra-dense cores left behind by the most massive stellar explosions, will undergo a similar cooling process, but with their own particular strangeness. A neutron star is an object roughly the mass of our Sun, compressed into a sphere about 20 kilometers across. A teaspoon of its material would weigh roughly 1 billion tons on Earth. Its surface gravity is so intense that light bends noticeably as it passes nearby. In the degenerate era, these objects will radiate away their remaining heat and settle into cold, silent density. They may occasionally collide with other dead objects in the rare gravitational encounter, producing a brief flash of energy in an otherwise lightless cosmos. But these events will become rarer and rarer as the distances between objects grow with the expansion of space. And then there are the black holes, the gravitational monarchs of the dead universe. Every large galaxy has one at its center, a supermassive black hole millions or billions of times the mass of our Sun. In our own Milky Way, the central black hole, called Sagittarius, a star, has a mass of roughly 4 million suns. In the giant elliptical galaxy M87, the central black hole weighs in at 6.5 billion solar masses. These are the dominant gravitational objects in the cosmos, and in the far future, they will be the last thing standing. As the universe ages, as galaxies drift and merge, and their stars are flung into the void by gravitational interactions, more and more matter will fall into these black holes. Gravitational dynamics over immense timescales will ensure that most objects in a galaxy eventually either escape to infinity or spiral inward toward the center. The escaped objects will drift alone through the expanding void. The captured objects will be consumed. In 100 quintillion years, 100 billion years, most of the remaining matter in the universe will have been swallowed by black holes. The universe in the black hole era will be a profoundly empty place. Imagine a single supermassive black hole containing the mass of what was once an entire galaxy, sitting in perfect darkness. No stars orbit it, no light illuminates it. It is surrounded by nothing but an ever-expanding ocean of vacuum, and it sits there, for timescales that dwarf the entire current age of the universe by factors of trillions, silent, patient, slowly evaporating. But even black holes are not eternal. In 1974, Stephen Hawking made one of the most surprising predictions in the history of theoretical physics. He showed that black holes are not perfectly black. They radiate, not light, not in the traditional sense, but a faint quantum mechanical glow, now known as Hawking radiation. The process arises from the peculiar behavior of quantum fields near the event horizon, the boundary beyond which nothing can escape. Virtual particle pairs are constantly popping into existence and annihilating throughout the universe, a consequence of the uncertainty principle. Near the event horizon of a black hole, one particle of a pair can fall in while the other escapes. The escaping particle carries away a tiny bit of the black hole's energy, and over time, this slow leak causes the black hole to shrink. The rate of Hawking radiation is inversely proportional to the mass of the black hole. Smaller black holes radiate faster. A black hole with the mass of our Sun would take roughly 10 to the power of 67 years to evaporate, a number so large that writing it out would fill pages. A supermassive black hole, the kind that lurks at the center of a galaxy, would take approximately 10 to the power of 100 years. That is a 1 followed by 100 zeros, a Google years. A timescale so far beyond human comprehension that it exists only as a mathematical abstraction. To put that in some kind of perspective, the current age of the universe is roughly 1.38 times 10 to the power of 10 years. That is 13.8 billion. The time for a supermassive black hole to evaporate is 10 to the power of 100. The ratio between these two numbers is so enormous that no analogy from human experience can capture it. If you compared the current age of the universe to a single second, the evaporation time of a supermassive black hole would be longer than the current age of the universe by a factor of roughly 10 to the power of 90. It is a number that exists beyond imagination. And yet, the process is relentless. Each moment, each quantum fluctuation at the event horizon shaves off an imperceptible fraction of the black hole's mass. The black hole does not feel it. It does not care. But over unimaginable stretches of time, the loss accumulates. The black hole shrinks. Its temperature rises. As it gets smaller, it radiates faster, which makes it shrink faster, which makes it radiate faster still. The process accelerates near the end. The final moments of a black hole's life are a burst of increasingly energetic radiation, a last gasp of particles sprayed into the void, and then it is gone. The structure that was once the most powerful gravitational engine in the universe simply ceases to exist. But time is patient. The universe has nothing but time. And eventually, even the most massive black hole will radiate away its last quantum of energy and vanish in a final faint burst of particles. The last light in the universe will not be the death of a star. It will be the evaporation of a black hole. And when that last photon escapes, the universe will have produced its final act of thermodynamic theater. There will be no curtain call. After that, the universe enters what cosmologists call the dark era. And this is where the story of cold reaches its ultimate conclusion. In the dark era, no normal matter remains. If proton decay occurs, and many grand unified theories of particle physics predict that it does, then even the subatomic building blocks of atoms are unstable over sufficiently long timescales. The estimated half-life of a proton is at least 10 to the power of 34 years, and possibly much longer. But in the dark era, where timescales stretch to 10 to the power of 100 and beyond, even the most stable particles would eventually disintegrate. Protons would decay into lighter particles. Neutrons, already unstable outside of atomic nuclei, would follow. The atoms themselves, the fundamental units of chemistry and structure, would dissolve, into a thin soup of electrons, positrons, neutrinos, and low-energy photons. Think about what that means. Every atom of every element that has ever existed, every carbon atom that was once part of a living thing, every iron atom that was once inside a star, every hydrogen atom that drifted through the void for billions of years, all of it would eventually come apart. The periodic table itself would cease to be relevant. Chemistry, the science of how atoms combine and interact, would become a historical curiosity with no remaining subject matter. The building blocks of matter would dissolve into their constituent parts, and those parts would disperse into an ever-expanding emptiness. The universe would be a vast, almost perfectly empty expanse, populated only by the faintest of particles drifting through an ever-expanding void. The temperature would hover just barely above absolute zero, sustained only by the last traces of the cosmic microwave background, now stretched and cooled to an almost inconceivable degree by the relentless expansion of space. Where there were once 400 photons per cubic centimeter, there would be fewer and fewer, their wavelengths stretched to kilometers, then thousands of kilometers, then millions, by the expansion of the universe. The temperature of the cosmic background would have dropped from 2.725 Kelvin to a fraction of a Kelvin, approaching but never reaching the absolute zero that the laws of physics forbid. And here is one of the most haunting details of this future. The accelerating expansion of the universe means that the observable universe will shrink over time. Distant galaxies, already receding from us faster than the speed of light, will continue to accelerate away. Their light will be redshifted beyond detection. One by one, galaxies that we can see today will fade from view, their photons stretched to wavelengths longer than the observable universe itself. A hypothetical astronomer in the far future, peering out from a dead galaxy, would see nothing. No other galaxies, no cosmic microwave background, no evidence that anything else had ever existed. They would inhabit a universe that appeared to consist of nothing but their own island of cooling matter, surrounded by a perfect, featureless void. The entire history of the cosmos, the Big Bang, the formation of the first stars, the evolution of billions of galaxies, would be invisible to them. The evidence would have been carried beyond the horizon by the expansion of space itself. No chemical reactions could occur, no structures could form, no energy could be extracted from the environment to perform any kind of work. The entropy of the universe, the measure of its disorder, would approach its maximum value. Every bit of usable energy would have been spent, every temperature difference equalized, every gradient smoothed out. The cosmos would be in thermodynamic equilibrium, a state of perfect uniformity, a state in which, by definition, nothing interesting can ever happen again. To understand why this is truly final, consider what it means for something interesting to happen. Every process that we would recognize as an event, a star forming, a planet cooling, a molecule assembling, a thought occurring in a brain, requires a flow of energy from a region of higher concentration to a region of lower concentration. It requires a gradient. A waterfall cannot generate power if the water at the top is at the same height as the water at the bottom. A heat engine cannot do work if the hot reservoir and the cold reservoir are at the same temperature. And a living organism cannot metabolize food if its internal chemistry is in equilibrium with its surroundings. Life in the deepest thermodynamic sense is a process that exploits thermal gradients. We eat concentrated chemical energy, we perform the work of being alive, and we radiate waste heat into a cooler environment. When there is no cooler environment, when everything is the same temperature everywhere, the process stops. Not because something prevents it, but because there is nothing left to drive it. This is the heat death of the universe. And despite its name, it is not about heat. It is about the absence of heat. It is about the final, irreversible victory of cold over warm, of disorder over order, of equilibrium over complexity. It is the moment when the universe exhausts its capacity for change and settles into an eternal, featureless quiet. The name heat death was coined in the 1850s by William Thomson, the same Lord Kelvin who gave us the absolute temperature scale. He and the German physicist Rudolf Clausius were the first to grasp the full implications of the second law of thermodynamics. Clausius stated it most memorably in 1865. The entropy of the universe tends toward a maximum. Entropy, in the simplest possible terms, is a measure of how spread out and disorganized energy has become. A hot cup of coffee in a cold room has low entropy. The energy is concentrated in the cup. As the coffee cools and the room warms, the energy spreads out. Entropy increases. When the coffee and the room reach the same temperature, the energy is as spread out as it can be. Entropy is at its maximum. No more useful work can be extracted from the system. The process is over. The universe is the cup and the room. The stars are the hot coffee. The void is the cold air. And the second law tells us that the energy will spread out. The hot objects will cool. The cold objects will warm, if only by imperceptible fractions. And eventually, everything will reach the same temperature, the same featureless uniform maximum entropy state. The coffee is cooled. The universe is done. What made this realization so disturbing to the Victorian scientists who first encountered it was its universality. The second law does not just apply to cups of coffee. It applies to everything. Stars, galaxies, civilizations, life itself. All of it is driven by temperature gradients, by differences in energy concentration, by the flow of heat from hot to cold. When those gradients vanish, so does the capacity for anything to happen. The heat death is not a dramatic explosion or collapse. It is simply the moment when the last temperature difference is erased and the last thermodynamic process runs to completion. The philosopher Bertrand Russell once wrote about this fate with a kind of mournful eloquence. He said that all the labors of the ages, all the devotion, all the inspiration, all the noonday brightness of human genius are destined to extinction in the vast death of the solar system. He was talking about the death of our sun, but the sentiment extends to the death of the universe itself. Everything we have built, everything we have thought, everything we have loved exists within a brief window of warmth in an eternity of cold. And yet, there is something in that truth that is not entirely bleak, because the cold is not an enemy. It is the default. It is the natural state of the universe. The cold was here before the first star ignited, and it will be here long after the last one fades. What is remarkable, what is extraordinary, what is almost miraculous, is not the cold. It is the warmth. It is the fact that in a cosmos trending inexorably toward equilibrium, pockets of intense, beautiful, complex warmth arose. Stars formed. Planets cooled to just the right temperature. Chemistry happened. Life emerged. Consciousness flickered into existence. Beings appeared who could look up at the sky and wonder about the temperature of the void. Consider the chain of events that had to occur to produce a single warm moment in your life. A cloud of hydrogen had to collapse. Nuclear fusion had to ignite. A star had to burn for billions of years, forging heavy elements in its core. That star had to die, scattering those elements into space. Another cloud had to form from the debris and collapse again. A second star, our sun, had to ignite. A planet had to form at precisely the right distance, with precisely the right atmosphere, to maintain liquid water on its surface. Chemistry had to occur over billions of years, building molecules of increasing complexity until self-replicating structures emerged. Evolution had to sculpt those structures into organisms, then complex organisms, then organisms with nervous systems, then organisms with consciousness, then organisms capable of wondering why the universe is cold. Every step in that chain required specific temperatures. Too hot, and complex molecules break apart. Too cold, and chemical reactions cease. The window of temperature in which life can exist is extraordinarily narrow compared to the full range of the cosmos. We are thermal Goldilocks, inhabiting a sliver of the temperature spectrum so thin that it is almost invisible from the cosmic perspective. And every moment we spend alive, every thought we think, every emotion we feel, is powered by the gentle thermal gradient between our sun and the cold of space. That gradient, the difference between the 5,800 Kelvin surface of the sun and the 2.7 Kelvin background of the cosmos, is the engine that drives all life on Earth. Without it, there would be no photosynthesis, no weather, no water cycle, no food chain, no civilization. We do not just live in the warmth, we live because of the warmth. We are made possible by the fact that the universe has not yet reached thermal equilibrium. We are the anomaly, not the cold. The cold is ordinary. The cold is expected. The cold is the rule. But we are the exception. We are the brief, improbable spark of warmth in a universe that does not require us, does not expect us, and will not remember us when we are gone. And perhaps that is the most terrifying truth of all. Not that space is cold, but that our warmth is so rare, so fleeting, so cosmically insignificant, and yet so fiercely, stubbornly real. We exist in defiance of the cold. Every heartbeat, every thought, every breath is an act of rebellion against the thermodynamic destiny of the universe. We are warm things in a cold cosmos, and the fact that we are here at all is the most extraordinary thing that has ever happened to the temperature scale. So the next time you step outside on a cold morning and feel the chill on your skin, remember this: you are not just feeling the weather, you are feeling the universe. The same force that will one day silence the last black hole and scatter the last proton is the same force that makes your fingers numb in December. The cold of your morning commute and the cold of the heat death are different only in degree, not in kind. They are the same phenomenon, playing out on vastly different scales. And the warmth you feel when you step back inside, when you wrap your hands around a hot cup of coffee, when you sit by a fire or stand in a shaft of sunlight, that warmth is not ordinary. It is extraordinary. It is the product of nuclear fusion in a star 93 million miles away. A star that will itself one day go cold. Every photon of warmth that touches your skin has traveled 8 minutes through the vacuum of space, crossing 93 million miles of nothing, to deliver a tiny packet of energy from the nuclear furnace of the sun to the surface of your face. Think about the journey that photon has taken. It was born in the core of the sun, where hydrogen nuclei are crushed together at temperatures of 15 million degrees and pressures of 250 billion atmospheres. The fusion reaction that created it released a burst of gamma radiation, a photon of extraordinary energy. But that photon did not travel directly to the surface. The interior of the sun is so dense that a photon can travel only a fraction of a centimeter before being absorbed and re-emitted by another atom. The path from the core to the surface is a random walk, a drunken stagger through the solar interior that takes, on average, roughly 100,000 years. The photon that just warmed your face may have begun its journey inside the sun, before modern humans existed. It bounced and scattered through layer after layer of hot plasma, gradually losing energy, shifting from gamma-ray to X-ray to ultraviolet to visible light. And when it finally reached the surface, it burst free into the vacuum and traveled to Earth in 8 minutes flat. You are being warmed by a photon that is 100,000 years old. You are being warmed by a star, right now, in real time. And that star is one of the last of its kind. In the deep future of the cosmos, there will be nothing left to do what the sun does for you every morning. The warmth you feel is borrowed. All of it, every degree, every calorie, every joule, borrowed from a universe that is slowly, patiently, inevitably asking for it back. Our sun has already burned through roughly half of its hydrogen fuel. In about 5 billion years, it will exhaust the hydrogen in its core and begin to swell into a red giant, expanding to engulf the orbits of Mercury and Venus and possibly Earth. The oceans will boil away. The atmosphere will be stripped into space. The surface of the planet will be sterilized, every trace of life erased, every monument and memory and molecule of human civilization reduced to plasma in the outer atmosphere of a dying star. And then the sun will shed its outer layers, forming a planetary nebula much like the boomerang, and its core will contract into a white dwarf, a dense, Earth-sized ember that will cool over trillions of years until it radiates nothing at all. That is the fate of our warmth, not just the warmth of the sun, but the warmth of every star that has ever shone, every photon of starlight that has ever warmed a planet, every nuclear reaction that has ever produced energy, every moment of thermal comfort that any living thing has ever experienced. All of it is temporary. All of it is a brief spike on an otherwise flat thermal graph that extends from the Big Bang to the heat death. We are living in the spike. We are the spike. And the graph is already returning to baseline. There is a strange comfort in this, if you are willing to look for it. The cold is not malicious. It is not a force of destruction. It is simply the equilibrium state of a universe governed by the second law of thermodynamics. The cold does not seek to end warmth any more than a river seeks to reach the sea. It flows. It follows the gradient. It moves from possibility to certainty, from order to disorder, from concentrated energy to diffuse energy. And along the way, in the brief interval between the concentrated state and the diffuse state, complexity arises, stars form, chemistry happens, life emerges, minds awaken, stories are told, and then the interval ends and the equilibrium resumes. There is a thought experiment that helps put our temporal position in perspective. Imagine compressing the entire history of the universe, from the Big Bang to the heat death, into a single calendar year. On this cosmic calendar, the Big Bang occurs at midnight on January 1st. The first stars ignite in mid-January. Our sun and the Earth form in early September. The first life appears on Earth in late September. Dinosaurs roam the planet in late December. All of recorded human history, every empire, every war, every invention, every love story, fits into the final seconds of December 31st. And the heat death? It does not fit on the calendar at all. The calendar would have to extend for trillions upon trillions of pages beyond December to reach the era when the last black hole evaporates. Our entire existence, the entire stelliferous era, is a brief flicker near the beginning of an unimaginably long story. and the vast majority of that story takes place in darkness and cold. We are living in the opening scene of a very long and very quiet film. The lights are on now. The stage is full of stars. The actors, the planets and the galaxies and the living things are performing their parts with vigor and beauty. But the second act, the long act, the act that occupies almost all of the remaining runtime, is a story told in the dark. No soundtrack, no audience, just the slow and silent spreading of energy across an empty cosmos until every last temperature difference has been erased and nothing remains but the faintest possible hum above absolute zero. We are the stories that the universe tells itself during the interval. We are the patterns that complexity weaves in the gap between the initial state and the final state. We are the universe's way of experiencing its own brief warmth before the cold returns. And the fact that we can contemplate this, the fact that matter organized itself into a configuration that can ponder its own thermal destiny, is perhaps the most extraordinary thing that any arrangement of atoms has ever accomplished. The universe is far colder than our minds are designed to understand. And the warmth we know, the warmth we live in, the warmth we are, is the rarest thing in existence. Treasure it, because the cold is patient. And in the end, the cold always wins. But the cold does not know it has won. And we do. And there is something in that knowing, something in the act of understanding both the warmth and the cold, that matters more than the temperature of any star or void or dying nebula. We are the universe's way of noticing its own temperature. We are the brief, improbable moment when the cosmos looked at itself, felt the cold on its skin, and chose to call it beautiful. And that may be enough.